In part 2 of lecture 3, we worked very hard to derive the master formula for soft limits. Now, we are going to use it to get some interesting results, in particular for soft photons and soft gravitons. So here comes part 3 and the final part of lecture 3. Now, I've written out here the master formula, and it depends on various angles and square spinor combinations, and these complex deformation parameters z and epsilon. They allowed us to pick out exactly the contributions that were divergent as epsilon goes to 0, and let me remind you that we assume that z is less than epsilon, and I know I'm abusing notation a little bit because I told you that c and epsilon were complex, so think about this in terms of magnitude. They are some quantities that are small, but as epsilon is taking to 0, z must be taking to 0 too. And again, as I mentioned at the end of the previous lecture, it might puzzle you a little bit to see the explicit z dependence in this formula. The variable a that appears here, well, it's just a constant. It depends on the mass dimension of the coupling between the soft particle and particle k, as well as the spin of the particle that we're taking soft, the helicity of the particle we're taking soft. Now, let us assume that the particle that we're taking soft is a photon. So we're now going to look at soft photons. So we have we assume positive helicity from the beginning of the derivation, and so we have a positive helicity photon. Let's also assume that the photon couples canonically as it does in QED, which means that it's a renormalizable theory with a dimensionless coupling. So the mass dimension of G is 0. This means that the number A is 0 plus 2 times 1, that's 2. So let's plug this into the formula and see what we get. So looking at our formula here, we will have that 2 times 1 minus 2, this gives 0, so we can ignore this term completely with the square bracket sk. We'll have that 1 minus a is minus 1, a minus 1 is equal to 1, and 2 minus a is equal to 0. And so writing out our master formula for this case then gives that a n plus 1 hat of c of epsilon is equal to the sum over k equals 1 to n of gk. The square bracket is to the 0th power, so that's 1. We'll have an epsilon times a z in the denominator and an angle bracket xs. And then we'll have in the denominator also 1 minus z over epsilon xk angle bracket sk angle bracket. And the only thing that was left in the entire numerator was a n hat of z. Now with the canonical coupling, we'll have something like whatever this particle is that couples with coupling gk, but it's the same particle that goes in and out, so therefore there's no change, and I can drop the k index on the shifted amplitude. Very good. You look at this, and you get concerned, because as I take the limit epsilon goes to 0, I see that z goes to 0 faster, and that means that there's a pole in 1 over z. But that can't be right. If I keep epsilon finite and take z to 0, this is a pole that appears in an unphysical place. That should not happen. The amplitude can only have poles where physical particles are exchanged. And those physical particles are exchanged at poles, which we know now in the shifted amplitude are at epsilon equal to epsilon k for each k. So there's obviously a problem here. I have the problem that I appear to have unphysical pole. in fact, any pole in the z variable at z equal to 0 would be unphysical. Therefore, it must be that when summed over all k, the residue at the 1 over z pole must vanish. It must vanish when summed over all the different k's that we have in our sum. What does that take? Well, let's compute that residue. So basically, I have my 1 over z pole there. I set z equal to 0 everywhere else. That means I set z equal to 0 here, and I set z equal to 0 there. And what I end up with is then the statement that the residue of that pole is the sum over k equals 1 to n of gk times an evaluated at z equal to 0, which means that I can remove the hat on this a. So it's just the unshifted n particle amplitude divided by angle bracket xs. But the an and the angle bracket xs do not depend on k, and so if this is to add up to 0 for the residue to vanish, then it must be that the sum over all the couplings of whatever our soft photon couples to must add up to 0. What does this say? It says that the sum over whatever of the couplings of the photon to the other particles must add up to 0 in any physical n-particle amplitude. But that makes perfect sense, of course, because that is just charge conservation. So without having assumed that there are things called electric charges, we see that whatever a photon coupled to with a dimensionless coupling must be something that satisfies charge conservation. There is no other choice by consistency, as you can tell from this master formula. That is kind of a fundamental result that it might be a little surprising to see come out of this hard work, but is nonetheless true. So now, with that imposed, charge conservation, can we then take a look at this formula again and ask what happens in the epsilon going to 0 limit? Now we have established that there was no z-pole after all, because charge conservation ensured that the residue of the sum over all terms at z equal to 0 vanishes. So now let's extract from this term what you get in the limit as epsilon goes to 0 when z is less than epsilon, and epsilon can still be taken small. This means that I can expand what sits inside this term here. And so when I do that, I get the following. We get that 1 over the term 1 minus z over epsilon x k angle bracket with sk angle bracket is of course approximately 1 plus c over epsilon xk sk plus higher order terms. These higher order terms won't matter. Well, they do matter, sorry, but let me just ignore them for the time being. But they don't matter for anything that I'll talk about right now. And so what I see is that when I plug this expansion back into the formula here, the z-poles will vanish by this one. This term now vanishes by charge conservation, as we saw before. And now I can see that the z will cancel with this over c, this part over c, and I get instead a 1 over epsilon pole. This becomes 1 over epsilon squared. Z dependent has cancelled. From over here, I get xk. Then I divide this by sk times another term which sat here, which was angle bracket xs. And that then multiplies the unshifted amplitude evaluated at 0. And so again, that means I can remove that explicit hat. Why is this familiar looking? This is familiar looking because this term is exactly the thing that I called S0 when I first told you about the soft photon theorem. This is the leading soft photon factor. In fact, just to remind you of the familiarity, this is xk. If I multiply this soft factor by ks square bracket, I'll get xs times angle sk times ks. And now you see that this becomes x k angle square bracket with s square divided by xs times pks squared, which I can also write as 2ps dot k. And what sits in this piece here, up to factors of square root 2 and minuses and so on, this is basically epsilon s dot k. With some x now, we recognize this x here as exactly the reference spinor of the epsilon plus mu polarization vector. Okay, so that was why this result was familiar. In fact, as we did this deformation of the momenta in order to ensure that our poles got moved all the way from epsilon 0 by this z shift, we introduced this reference spinor x for that purpose, and now we see that that x is exactly the reference spinor of the polarization vector of a soft photon in this context. That came out completely automatically. So very nice, we've derived the leading soft photon theorem. How do I get the subleading soft photon theorem? Well, when I look at this term, the subleading soft photon theorem with S1, this arises from cancelling the 1 over c by writing a z k, so a n of z, as a n at c equal to 0. This gave the leading S0 part. But then there's a subleading part, which is z times the z derivative of our amplitude evaluated at c equal to 0. Of course, dot 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 dot, which won't matter. And this particular limit is very relevant because this derivative will be converted into a certain spinor helicity derivative, which can be related to the angular momentum operator, and that's exactly what sits inside that soft factor. I'm not going to write it out explicitly because we're not going to need it here, but you can find it in the references that I will provide for you. Okay, so this is a lot of stuff that we got out. We got the leading soft photon theorem out of the master formula, and we also learned that we must have a situation where charge conservation always holds for amplitude, so we derived that water density automatically. Now let's shift our attention to gravitons. So gravitons have spin 2, and we look at the positive velocity gravitons turn soft, so Hs is going to be 2. Now the right coupling dimension to consider in this case is a coupling dimension which is -1. That's how gravity self-couples, as we know from GR. And as we discussed, by the way, when we computed the amplitudes from the how spinor helicity fixed the free particle amplitudes. Now what is A in this case? It's the mass dimension of the coupling plus 2 times the helicity. So that's -1 plus 2 times 2. That amounts to 3. So what does our master formula now give in this case? So here it is magically appearing. And now let's see how we can apply it. So 2 times Hs is 4 minus 3. So that means that this whole factor amounts to simple 1. 1 minus A is going to be -2. A minus 1 will be 2. And then 2 minus A is going to be -1. Alright, so let's write this out and see what we end up with. So we have an plus 1 is the sum over k equals 1 to n of whatever the coupling is from the graviton to the kth particle. And all I've assumed is that this has dimensionality -1. I've not assumed anything else about it. I have square bracket sk. This will get multiplied by an angle bracket sk from down here. And divided by epsilon times z squared times xs squared. And this is multiplied in the numerator by ak, the n particle amplitude deformed at c, divided by 1 minus z over epsilon x k angle bracket divided by sk angle bracket. Plus, of course, order epsilon terms that won't matter. Epsilon to the 0th term, I should say. That won't matter as I take the limit. So let me actually go back and correct this, since it should say so correctly everywhere. All right, very good. Epsilon to the 0th. All right, so this is what we have for gravitons. We immediately discover that there's an issue here that appears to be a 1 over c squared pole. As we discussed before, this is entirely unphysical. The physical amplitude cannot have any poles in an unphysical place such as z equal to 0. And so the residue of this pole must vanish. So let's compute that residue. So 1 over c squared residue, what do we get? Well, we want it to vanish, so we should acquire that 0 is equal to the sum over k equals 1 through n of gk times, and then we have square bracket sk times angle bracket sk multiplied by the amplitude evaluated at 0, and nothing changes in that, so we can drop the label k. And then we have 1 over epsilon, and we have xs squared, as well as nothing from this angle bracket. Now, taking away things that don't depend on k, this is equivalent to requiring that 0 is equal to the sum over k equals 1 through n of sk square bracket times sk angle bracket and multiplied by gk. So what does it take for this to vanish? Well, in fact, this is the same as interchanging the argument here in s and k, of course, because the overall thing just has to be 0, so I can write this as ks without any change of the constraint. And then I see that what is sitting right here is just pk. And so if it were that all these couplings were all the same, then this expression would vanish simply by momentum conservation. If these are all the same, this expression, this sum, vanishes by momentum conservation. Because the unshifted k momenta, of course, satisfy momentum conservation for n particles. So, requiring that all the gk's are the same, let's call that same kappa, then that is exactly the same as the statement that the graviton must couple to every other particle in the spectrum. Whatever they are, the graviton must couple to it, and it must couple to it with exactly the same coupling, kappa. And that is exactly the Amplitudes version of the equivalence principle. And this is very particular to gravity. This doesn't happen for, say, gluons. Gluons will couple to things that carry color charge, but say electrons and muons and taus don't. And for that reason, the gluon will not couple to them. So, on the other hand, a graviton couples to everything, no matter what they are, and it does so with exactly the same coupling. And that's what makes gravity very special, and that's what is really encompassed in the Amplitudes version of the equivalence principle. Alright, so this is sort of a fantastic outcome of a very simple thing, namely the statement that this master formula cannot be allowing the amplitude to have a pole at z equal to 0, that's unphysical, it must vanish, that gives us the equivalence principle. But this was a 1 over c squared pole. We need to worry also about what happens when I expand these factors, both the a and this other factor, and try to cancel the z pole. What about the 1 over z? And it's actually not that bad. Nothing much happens. If I look at the formula here and I expand in small z over epsilon, then I'll find that I cancel a factor, and let me highlight them. I cancel a factor of sk, angle bracket, but I replace it with an xk angle bracket. And so, given that I already have the equivalence principle, the equivalent statement now becomes that the sum over k through n times kappa, which is my coupling, times square bracket ks, times angle bracket kx must vanish in order for this residue to vanish. But this also just holds by momentum conservation. It did not need the x to be s, this will hold anyway, so the 1 over z pole is automatically okay. There's not going to be a pole, it will cancel in the sum. You might ask the same thing from the order z term that will arise from the expansion of the amplitude, but that similarly is not a problem. Very good. So what happens is now that the order z to the 0th term are the ones that are going to give the soft factors. And those order z to the 0th term will give the soft factors that in the first part of lecture 3 I called curly S0, curly S1, and curly S2. These are universal factors that arise from the soft limits. They will come at order epsilon cubed, 1 over epsilon cubed, 1 over epsilon squared, and 1 over epsilon. And they can all be derived explicitly from the master formula. For now, let me just show you how the leading order term comes out. So let us take a look at our expression here that we have for gravity. I'll copy that and show you how curly S0 arises. Now the term that I have here in the denominator is something that I can expand. 1 divided by 1 minus z over epsilon xk over sk is the same as 1 plus z over epsilon xk divided by sk angle bracket plus z squared over epsilon squared xk angle bracket squared divided by sk angle bracket squared plus higher order terms, which are not relevant for what we'll do. And this then, when I multiply it in here, and I expand this to piece to go to just have at z equals 0, then I find the following. I find that a plus n as a function of z on epsilon becomes the sum equals k equals 1 through n. We now know that the coupling here should be kappa for all k. Then I have square bracket sk times angle bracket sk, and I get xk squared from divided by sk squared times xs squared from right here. The z squares cancel, and I end up with an overall 1 over epsilon to the cubic power, because I have 2 powers of epsilon from this term and 1 from that one. By the way, this term here, this was what would be vanishing, has vanishing residue. That was the one I took before, it was the 1 over z pole. So I get the 1 over epsilon cubed contribution from this term together with this epsilon. These z's cancel, I have z to the 0. And what you see here is this is exactly the soft factor. This is sort of in quotation mark, this factor squared times the energy. And in the first part of lecture 3, this was exactly what I told you was the soft factor. And by the way, I forgot here an an of 0. And so this is exactly curly Sn times an. And that was what we set out to prove. Now, the curly S1 and curly S2 is what you get from expanding out terms that give you order z to the 0 by also expanding out the amplitude an in powers of z. That will give you a 1 derivative term, which gives you the subleading soft theorem, and a 2 derivative term that gives you the subleading soft graviton theorem. So this is pretty cool. The soft graviton theorems follow from the same master formula, and the equivalence principle came out for free. I advertised one more property for you, well actually 2 more, but I'm only going to show 1 here, and I'll add the rest in the notes. And that is now about not being allowed to have higher spin. So I want to illustrate to you how this is prohibited by this simple master formula. And I'll do so simply in an example, and one can do a more thorough thing, which we did in our paper with Jones and the Schulich from 2016. So suppose we have spin 3. So massless particle, and we'll consider one we take soft, which has helicity plus 3. Suppose that there is some coupling in the theory that couples this particle with spin 3 to another particle with spin 3 but the opposite helicity, as well as a positive helicity graviton. What would the coupling of such a particle be? Well, it would be 1 minus the sum of the helicities, so that's minus 3 plus 3 minus 2, that amounts to minus 1. And then, since Hs is 3, this gives us that the number 8 that appears in the master formula is 1 minus 2 times 3, which is 5. So when A is 5, the master formula will give us a very high order z-pole. So let's go back and take a peek at our master formula again from the beginning. Here's what it is. And now, with A equal to 5, we see that we have a pole which is order z to the 4th. Again, this is unphysical, and so its residue must vanish. So the 1 over z to the 4 pole must have vanishing residue. In other words, there must be no pole. There cannot be allowed to be a pole. All right, so what does all of this give? So 2 times the helicity of S, that was 3, so that gives 6, minus 5, this amounts to 1. Here I have 1 minus A, that gives minus 4, but that's not so relevant because nothing here depends on K. I have 2 minus A here, that gives minus 3, and then I'm setting Z to 0, so I don't have to worry about this part. So I end up with a situation where the residue, the 1 over C to the 4 residue, will give me a condition that 0 must equal the sum over K equals 1 through N of GK of square bracket SK times angle bracket SK cubed. There's also a dependence on the angle bracket XS, but nothing depends on K there, so I can ignore it. Likewise, there could be a dependence here on AKX of Z. But you see that there's nothing here that will make this vanish. I can't just take all the couplings equal because I have a cubic power there. It would require some very special miracle for this to vanish that would depend on details inside the n-particle amplitude, and that's going to be impossible to do. So generically, what sits here is always going to be different from 0, and therefore a massless spin p particle cannot couple to a spin 2 particle. And I should say massless, emphasize the masslessness of this. And in general, one can prove and use the master formula to prove more generally that any massless spin S with spin greater than 2 cannot couple consistently to the graviton. At least not through cubic couplings, for which this amounts to. And we know in particular that the graviton is supposed to couple uniformly to any other particle. And so if there were such particles, they would couple the same coupling, and this thing can just never be 0. So I advertised one more property for you in the earlier parts of the lecture, namely that a gravitino must couple supersymmetrically to the graviton if it's interacting. And this follows from a combination of the equivalence principle and the master formula. And I will simply write out the notes for this, but I won't record it in the lecture so you can read it if you're interested in the PDF version of the file. But for now, I just want to end by saying that you get very fundamental results out of the master formula. Very fundamental results arise from studying the soft limits. And soft limits have played a big role in many contexts. By the way, we're not the first ones to argue that the equivalence principle comes out from the soft theorems. This has been done in many other contexts before. But it's a nice way of collecting all the different soft theorems, including the subleading soft theorems and these fundamental statements, into one big nice master formula that is derived applying these complex analysis ideas that I've shown you. And I hope this gives you a little bit of a flavor of some of the technicalities in the subject and how powerful it can be getting to derive some of these very fundamental results. And with that, I'll end lecture 3, and we'll return in lecture 4 to study a different subject, namely the double copy.